Yes, am I audible? Hello. Hello.
So just wait, we'll just start in a few minutes, okay? I think persons are still joining. So just give them some time so that they can join and then we can start the session, right? Okay, I hope I am audible. Hello. Yes, hello. Am I audible? Hello. Just reconfirm if you can see my slides and my screen is also visible. Because some persons were facing some issues joining the link. I don't know why. Joining through the MS Teams link. So if you have any suggestions, we can also shift these sessions to Google Meet. So I want to hear your suggestions. So kindly let me know. Okay. So what do you want? You are comfortable with Teams or you are facing some issue maybe in the joining the meeting or maybe some other issues in the interface? Just let me know. Yes. You can just unmute and let me know.
Yes, sir. Shift to the Google Meet.
Okay, shift to the Google Meet, right? Otherwise, maybe there may be some problems. Okay. So from next week,
Yes.
we'll just shift to Google Meet so that you guys are able to join easily. I understand that there may be a problem in the interface of the Teams. So
Yes, sir.
yes, so just be ready with a pen and paper because this week we are doing in Teams. Some people are also finding issue in joining the Teams link. I don't know why, but because I have conducted such sessions for over a year now, but this issue is happening for the first time. Maybe in WhatsApp there is some problem. All of you are in WhatsApp group, or should I send you the WhatsApp group link so that we can just keep updated and just be connected, right? So if you are not in the WhatsApp group, let me just add you to the WhatsApp group. And nobody is asking any doubts. I don't know why. So I will just place the links in the comment, right? You can just find the link of all the WhatsApp group and other things, the recorded sessions and
Okay,
all.
sir.
But I still want all of you to join the live sessions because otherwise you will not understand what we are being taught. Because in the recording everything is not clear because you cannot ask your doubts there, right? So I have posted in the comment the link and all those stuff where you can find the slides and what. So I will add also all of you to the WhatsApp group. Just click the link and you will get added. Okay. Because it
Okay,
is
sir.
important to stay connected and many of you are also facing problems in the link. So from next week we will just do in Google Meet, right? So without wasting any further time, I can see some persons are still to join but we cannot help because I have personally also messaged them, but I think they are facing some issue. Just
Good evening, sir.
good evening. You were asking or someone else were asking in the group?
Me also asking, sir.
So what happened actually? Can you please just briefly explain so that we can just understand what happened actually?
Nothing, sir. By clicking on that link, it shows hang out the MS Teams.
Oh, okay, okay. So MS Teams may be having some problem temporarily. So we'll just shift from the next session to Google Meet, right? Maybe that will help all of you, right?
Previous week also same thing, sir. After 10 to 15 minutes later, I was joined, sir. Previous week.
Okay, okay. So the link itself has some problem. See, link we are only generating. You are also getting the mails, but in the link itself there may be some problem, maybe connecting or something. So next session onwards, Google Meet, right? You'll get the updated links. Every week you get mails, right? That there will be live sessions. So you will get the updated link there. So keep following the mails, and I will also send you the link in the WhatsApp group of the session, right? So without wasting much time, uh, so just we will start the week 4 live session, and I also told you what will be the topics. The topics will be resonance, and then we'll go into bandwidth and quality factor, and then related problems in series RLC and parallel RLC networks, and then we'll just touch the three-phase AC circuits. Some basic problems we'll solve, right? That will be enough for week 4, right? So as you know, the sessions are being held every Tuesday, 7 to 9 p.m. And you also get updates in the WhatsApp group and mails from NPTEL about the sessions and the links also. So from next week, I'll just keep a note of it. From next week, we'll just shift to Google Meet, right? And all of you will be receiving updated link itself, right? In the mails every next session onwards, right? So we'll shift to Google Meet interface. So just for your reference, I want to know if you are facing some doubts or not, because none of you are joining on time, maybe because of the link issue. But I encourage all of you to join at least 10 minutes before, right? At least 10 minutes. Why? Because that will help you clear all your doubts, prevailing doubts, maybe some small doubts that we can clear, or some doubts again we can cover the concepts in those 10 minutes, and then we can just shift to the week content, right? Weekly content. So join 10 to 15 minutes, because I am available 30 minutes from 30 minutes before the session. You can join and request to join in to solve any problem or any concepts, right? So I prefer encourage that you join at least 10 minutes before, all of you, right? So that we can just discuss and be interactive, because these sessions are interactive sessions. If you don't speak up, then I cannot understand what are the doubts that are going on in your mind, because just simply solving problems will not help, right? There should be some interaction. So all of you join at least 10 minutes and stop me if you are not understanding anything, some concepts in midway, right? Anywhere midway between the sessions, so that I can just re-explain, and maybe that will be helpful, because I go sometimes fast, sometimes slow. I cannot understand where you are facing doubts. So you are encouraged to join at least 10 minutes before and just keep injecting your doubts between the sessions, right? And we are now at the week 4. You can see we covered the resonance part of the AC circuits, and then three-phase AC circuits. In resonance, there are a lot of things. So we'll simply cover everything one by one, right? So we'll just go into the AC circuits, and briefly we have also explained the AC circuits and how to deal with them, how to draw the phasor diagrams of the series parallel RL, RLC, and RC networks. All in the previous week. Now, like in this week, what we'll cover is the resonance phenomenon. There is one phenomenon in AC circuits. We don't see that phenomenon in the DC circuits, right? One phenomenon exclusively for the AC circuits, which is the resonance phenomenon, and the related concepts covering resonance. So up to this, all of you are able to see the slides moving and my voice audible, clear?
Yes,
Because
sir.
that's also one issue. So I am talking about resonance. Okay, so what you understand by resonance? Can any one of you just quickly tell me what you can understand about resonance?
Inductive reactance is equal to capacitive reactance. That's
Yes.
called as resonance.
Yes, so that is what you are being taught, that inductive reactance or capacitive reactance cancel each other out, and the circuit behaves like a simple resistive network. And from there the current is maximum, the impedance offered is minimum, and then some kind of resonance stuff you learn in 11 and 12. But actually there is no such cancellation happening from a engineer's point of view. If someone asks you what is resonance, you need to understand that for any combination, because in class 12 you learn about this kind of networks R, L, and C, right? And the AC excitation. Now the network can be more complicated, like for example more L and R and more C's. There also resonance phenomenon can happen. So in a briefly, I can speak in a generalized manner. What can you understand about resonance is that it is a phenomenon for a particular frequency. Okay, resonance, what is it? It is a phenomenon, okay, for a particular frequency of excitation. Okay, where the system natural frequency and the driving frequency of the source matches, right? So it is such a frequency with which when you excite, that means this excitation source, if you excite with that frequency the system, which is this, then what will happen? The system will, that is the natural frequency of the system, it will match, and the phenomenon will start. Now what is that phenomenon which you call as resonance? What is that phenomenon wise? That means we learned when it will happen. When the excitation frequency matches the natural frequency of the system. That is understood, that system has its own natural frequency, And when it is just like the 11-12, you heard about the many simple harmonic motion you have learned, and then the ringing the fork you have learned. So in all those cases, there is a natural frequency of any system. Any system has its own natural frequency. So when you match that frequency and force it, maybe excite it, then some phenomenon occurs. So one of those phenomena, electrical phenomenon, we can term it as resonance. So in resonance, what happens is the inductive and capacitive energy exchange matches. So there is no such cancellation. What happens only, because I told you in the previous week, the voltage, if you impress this kind of voltages, AC voltages, what will be the nature of current for the inductor? It will lag by 90 degree. So how will it look like this, right? And if you product both, then maybe what will happen with double frequency, positive, so like this with 2x, the reactive power of the inductor will look like this. But you know that this is IL, but IC, what will happen? It will lead by 90 degree. So for that, since it is leading, then how will the reactive power look like? It will be 180 degree reverse in phase. So you can draw that. See, voltage is like this, speaking in terms of phasor, but the inductive current is like this, and the capacitive current is like this. If you excite ideal L's and C's, then voltage, excitation voltage, if you are having some voltage and some L and C, then the IL will lag, but the IC will lead that voltage. So if you product the both, V and IL, you will get a 2x sinusoidal waveform. But that 2x sinusoidal waveform for product of VL and IL and V and IC, which you call as QC, V and IL, which you call as QL, will be 180 degree phase reverse. So when the inductor absorbs the energy, reactive power or whatever you term, the capacitor delivers that in one cycle I am speaking. So you can see for this particular moment of time when the inductor was absorbing, whatever you term, because there is no such significance of absorption or delivering the reactive power, because reactive power looks like this. In one cycle it comes, one cycle it goes. In one half cycle it comes, one half cycle it goes. And in a full cycle, there is no effect, right? So reactive power looks like this only. The active power looks like this with 2x, because you can understand, if you have V and you have I in phase, then only the reactive power will flow, then only the active power will flow, because V and I in phase will create the active power. Otherwise, no active power is there. Only when V and the component of I, which is in phase with V, creates the active power. Why active power? Because the active power needs to be delivered, needs to be unidirectional. But the reactive power is bidirectional. You can understand that, because it has a positive and negative. That means it comes and then goes. That is the nature of reactive power. But even in that, the inductive absorption of the reactive power happens when the capacitor delivers. So one time it delivers, one time it absorbs. Similarly, when the inductor absorbs, the capacitor tries to deliver. So resonance is a phenomenon when these two matches. What I'm trying to tell, can anyone understand? Exactly when it is matching. How much ever reactive power the inductor is in a function of time, how much ever reactive power the inductor was trying to deliver, when that much the capacitor was trying to absorb, then their effect nullifies. The circuit will behave like there was no inductor and capacitor. So that is the significance of resonance in particular frequency, which is actually equal to the system frequency or natural frequency. This phenomenon is observed, and the energy exchange matches. What will happen when energy exchange matches? Circuit behaves to be
pure resistive network.
Yes, completely resistive network, right? So you can understand that resonance is a particular operating point based phenomenon. Only when that frequency is attained, then only the resonance phenomenon is observed. So what can you just quickly asking you, what can you just comment? Because series RLC is the fundamental network, right? So we'll mostly see in terms of series RLC. So when the effect of L and C in a series RLC network at resonance, what can you comment? L and C?
Impedance is minimum, sir.
Yes, impedance. Why minimum? Because impedance Z is nothing but R plus J times omega L minus 1 by omega C. Now these two nullifies.
Net reactance is 0, sir.
Yes, no, this part is 0.
Yes, sir. Yes.
So what can I just simply say that I can short the L and C. So L and C totally behaves to be shorted only at resonance frequency, not for other frequency. But don't just, for the simplification or to analyze how the source will behave, we can just short L and C, but they are not out of the circuit, they are there, okay? Because when you try to find the current, you will find a current which is equal to V by R, because the reactance, yes, the reactance part is off, and V by I or V by R will be the current at resonance. However, the current still flows through L and C, and you can actually see that the voltage drop across L and the voltage drop across C will nullify each other because of the current. The same current is flowing. So I times J omega L and I times minus J by omega C, because of this omega to be 1 by root over LC, which we will derive, because you can see from there that when this matches, omega naught is nothing but 1 by root LC. For this frequency, what happens? Voltage drop across L and C are just opposite of each other, okay? Because of the minus sign. In magnitude terms, I am speaking.
So each other.
Yes, the one is just plus J, one is minus J. So both cancels out. So one more, I can write that voltage drop across L and C cancels, and voltage drop across R equal to supply voltage. Agree? Because if you just maybe write the KVL, if you write the KVL, okay, and go in the loop, then these two will cancel each other. Because I just showed you, these are because of the negation or the 180-degree phase reversal of the voltage drop across I and C due to their reactances offered. So V equal to VR. So this is also one more point. RLC network, the voltage drop across the resistance is nothing but the supply voltage. So complete supply voltage is virtually impressed across the resistance, because the inductor and capacitor totally behaves to be a short. It can be thought of as shorted for circuit simplification during solving the problems, and only at resonance frequency. Only at resonance, right? You can simplify the network like this, because of the cancellation of the impedances and the cancellation of the voltages across the inductor and capacitor, and we can model zero voltage by simply a short. I told you in the second week, we can model zero voltage by a short and zero current by a open circuit. Hope you remember, right? So we have actually coined the definition of resonance and just simply saw the result for series RLC network. Now, for series RLC network, likewise in parallel RLC also we will face resonance. So what we are actually trying to do, how we are actually deriving the resonance? We are actually deriving the resonance by seeing the reactance offered, right? And we are actually trying to equalize it to zero. Why? Because whenever resonance occurs, I told you by definition, the energy exchange between the inductor and capacitor matches, and the circuit effectively behaves to be resistive in nature. So if we overall if we see the total impedance that is offered by the network and try to equalize its imaginary part to 0. Likewise, we did this thing in this simple circuit. So we can find the resonant frequency, because that is the natural frequency of the system. And you can understand, if you can equalize it to 0, you can just, because this is only the frequency dependent part. So how to determine resonant frequency for any network? Just calculate the impedance and equate the imaginary part to 0. Net impedance across the source, right? Because this is the forcing function. So you can equate the imaginary part to 0, and likewise you can calculate the resonant frequency. So that is how you, so imaginary part of this Z can be equated to 0, or else imaginary part of Y also you can equate to 0. Why equate to 0? Because you can understand that either for Y or Z, if your circuit is purely resistive in nature, you will not face any imaginary part, right? And that is exactly the thing at resonance. There is no imaginary part either for the impedance or for the admittance, because the circuit behaves to be totally purely resistive in nature. So you can either do it for admittance or for impedance and equate it to 0. Now, where I told you the impedance thing will work better for series RLC circuit, because dealing with impedances are easier in series RLC circuit, and dealing with admittances are easier for parallel RLC circuit, right? So these are some basic things that you can do in order to make your calculations just simple, because in series RLC network, calculating the impedances, equivalent impedances are very easy. So you can deal with such things. But the overall concept is that at resonance, circuit or network completely behaves to be at unity power factor or resistive, purely resistive. So no question of imaginary part, right? That's why we are doing these small simplifications and minimizing our calculation so that we can quickly determine the resonant frequency, right? So up to this, it is clear?
Yes, sir.
So what I can do, so you can understand the concept of resonance up to this, that what is the behavior. Now there are some terms that are further introduced to make your understanding simple for this kind of problems. So there are two terms, the quality factor and the bandwidth. We'll see this for the series RLC network as well as for the parallel RLC network, and how to actually deal with those parameters and solve the problems. So what do you know about quality factor? Can anyone tell me? So I think people are not joining.
Omega L by R.
Yes, someone messaged me that class will start or not. Are you aware? You are only the person or someone else is the person? Just let me call them, okay? Just 1 minute, huh? Because I think people are still. Yes, I think I received a call from you. Are you able to join? Or so are you on a PC or a mobile device? Okay, mobile, right? So can you open MS Teams and then just go to the join a meeting, and from there you can just join, right? You get what I'm telling? No, I understand, but you can join from the Teams itself. That is what I'm trying to tell you. How you can join, because from the next week we are doing by just Google Meets, right? That will help you. But this week also you can join simply by clicking the 1 minute, okay? Just stay and we'll just admit few more persons.
Okay, sir. No problem.
Okay, I think you guys have joined, right? Yes, hello.
Yes, sir.
So what I was discussing is very simple, that when the resonance occurs, and the resonance I told is only a phenomenon which happens for one particular frequency, and that is the natural frequency of the system. So when your supply frequency matches the natural frequency of the system, then only the resonance phenomenon occurs. And how to find the natural frequency of the system? Because we know one thing, that at resonance, the circuit behaves to be completely resistive in nature. Because why completely resistive? Because the inductive and capacitive energy exchange matches, and due to the matching of them and the cancellation of the voltage across the L and C, by cancellation because of the difference in phases of the impedances. So the inductive and capacitive admittances cancel each other, and or otherwise you can say the energy exchange matches, and from there we can just simply short the L and C for a series connection, because the effect of L and C vanishes at resonance frequency and they cancel each other out, and the voltage drop across the L and C just equalize in opposite phases due to the phasor diagram, and we can model, because the VL plus VC is 0 and it cancels out, so we can model a zero voltage. How? I told you in week 2, we can model zero voltages using short. So that is how we are dealing with the series RLC resonant circuits. Up to this I explained. Okay, so after this we are going to the concept of quality factor and bandwidth. So to understand resonance much better, you can further simplify things using the two terms quality factor and bandwidth, right? So what do you understand by the term quality factor? It is usually denoted as Q. I want to hear from you. Okay, what do you understand by quality factor? Yes, please tell me, because you both should be interactive, right?
Energy stored in some inductor divided by total power dissipation into 2 pi.
Correct. So it is coined, it is defined, that term is defined as quality factor, but more correctly I will write it. It has various forms, so I'm writing it for you. Okay, so maybe this definition, yes. So quality factor I can write as 2 pi times maximum energy stored. Okay, divided by energy dissipated over a period of cycle at resonance. Okay, that means the maximum energy stored, you know what is the energy stored by L and C? It is half Li square and half CV square. The voltage across inductor, sorry, the voltage across capacitor is Vc. So we can write half CVc square as energy stored by capacitor, and energy stored by inductor is half Li square. IL I can write because the current through the inductor. So the maximum energy stored by the inductor, you can understand, and divided by the energy dissipated over a cycle. Now you understand that energy keeps on accumulating cycle wise because it is nothing but integral Vi. So over one cycle only we need the energy, and that too at the resonance. Okay, so that times 2 pi, it is defined like that. So what it means, further simplifying we can understand. Okay, so what will happen, 2 pi, leave it 2 pi, and then what you can do, energy is what, power times time or power divided by time? What is energy?
Power into time.
Correct. So it is maximum energy stored divided by power dissipated into time, but time is how much? Over one period, right? So multiply one time period, because we need only energy up to one time period or one cycle as per the definition. So only one cycle we multiply. Now what will happen? What you know, F naught is 1 by T naught. These are all resonant frequency or resonance time period. So this T naught is nothing but 1 by F naught, and this F naught goes off. So 2 pi F naught multiplied by maximum energy stored divided by power dissipated at resonance, as you can understand. This is nothing but power dissipated at resonance. So what is it? Omega naught times maximum energy stored divided by P naught. Up to this it is clear or not?
Clear, sir, clear.
So how you can further simplify it for a series RLC? I want to hear from you. For a series RLC network, what you can write as maximum energy stored? You know the current. For a series RLC network, what is the current? V by R, right?
Yeah.
I am drawing the network for you. So V is actually V cos omega t, okay? Because it is AC. So I is V by R cos omega t. Okay? So the current is like this. So what I can write? Maximum energy stored is half Li square. And power, what can you write about the power? Omega naught times half multiplied by L multiplied by I square. This is IRMS, okay, as you can understand. And power, what I can write? IRMS square multiplied by R, because this is the power dissipated over one cycle at resonance. Right?
Yes, sir, got it.
So what can you write? What it simplifies to?
Cancel out, sir.
Yes. But one thing you are missing. What I wrote, this is maximum energy stored.
Yes, sir.
So what is maximum energy stored? Half L I M
value, sir.
or I peak.
Converted
I
into
peak.
R.
This should be maximum energy stored, right? We need maximum energy stored at any point, right? So this should be I peak square, right?
Multiply with root 2, sir.
Correct. Or I am just writing I peak square. But what is this? Power dissipated is IRMS square into R. Correct. So there is a factor of 2 or root 2 working, right? So I peak square, you can write it as omega naught into half into L into, how can I write I peak? Root 2 times IRMS. Because this is I peak whole square divided by IRMS square into R as per definition. Okay. So what is quality factor boiling down to? Q equal to this 2 and this root 2 square, okay, will cancel out. And we are left with omega naught multiplied by L multiplied by IRMS square. But IRMS square also will cancel out. And we are left with omega naught L by R. This derivation is clear. This is useful for many places. Okay. So what is omega naught? We derived. Omega naught is nothing but because omega L equals to 1 by omega C at resonance. So at omega naught. So what is omega naught? 1 by root LC. This is the resonant frequency. So what can you write? That Q is nothing but omega naught L by R. Now further we can write more things. Okay. So what I am trying to tell, up to this what we know. V, I am writing as phasor representation. Okay. V angle 0 or V just you write. So quality factor is what? Omega naught into L by R. Similarly, omega naught resonant frequency is 1 by root LC. So how to determine? Just do imaginary part of Z equal to 0 for series
RLC
and
circuit.
imaginary part 0 for parallel RLC. Because why? At resonance
condition,
the network behaves
reactance
as
is 0.
Yes, reactance is 0. You are telling this term is only true for a series RLC network. Please remember this. Okay. So better term you can use is at resonance network behaves to be purely resistive. As L and C energy exchange matches. And their effect also nullifies. This you can tell, their effect nullifies. But whether to replace them by a short or a open, we will see how to decide it. I am telling their effect nullifies. Now for a parallel RLC network, their effect nullifies not by shorting but by opening. That we'll see what it happens, why it happens like that. But up to this, you can now understand that at resonance for a series RLC network, L and C can be shorted. Only for series RLC, okay? Understood? And quality factor is this. Now we can go further, okay? Now quality factor is this, what we can do, the current through both L and R are same. So what we can write, Q equal to omega naught L by R, multiply by I and divide by I, nothing changes. So what is this? And what is this? What can you write? Voltage across inductor by voltage across resistor, the mod of that. Yes or no? Agreed or not? I hope it is clear, right? Again, omega naught is 1 by root LC multiplied by L. This is omega naught, right? And Q is nothing but omega naught L by R. So what can you write? What can you write? What is voltage across capacitor? Current times. I am telling about the magnitude only. Current times omega 1 by omega C. Or I can write omega naught C for particular frequency omega naught. Agreed? So can you simplify and tell me what is the quality factor in terms of VC and VR? Q as a function of VC and VR, can you tell me? Just simplify and tell me. You know that omega naught L by R is Q, okay? From here, can you tell me Q as a function of VC and VR? Because Q as a function of VL and VR, I told you. What is it? It is nothing but VL by VR. What you can tell me?
Q equal to 1 by omega CR. 1 by omega c into r.
Okay, 1 by omega c into r. How you got it? You replaced one more thing I want to tell you. Omega naught is 1 by root LC. So you can write omega naught square is 1 by LC.
Yes.
So from here, you know Q equal to omega naught L by R, or you can write as omega L as, you can replace value of L as omega naught times 1 by C times omega square and divided by R. So from here, he actually derived 1 by omega naught CR. It is also Q. But I can tell you what? VC, you know, I by omega naught C. VR, you know, I into R. So what is VC by VR? 1 by omega naught C into R. So it is nothing but VC by VR. So voltage drop across inductor magnitude wise and voltage drop across capacitor at resonance, as you can see, are equal in magnitude but reversal in phase. So it is quality factor times VR, quality factor times VR. And I told you at resonance, since L and C cancels each other impedance wise and their voltage drop sums up to be 0, the voltage drop across supply and the voltage drop across resistance matches, and it is nothing but Q times V. Right? Q times V supply. So VR is nothing but V supply at resonance for a series RLC network, right? For a series RLC. So these derivations are very important for you to solve the problems or to find the quality factor easily for any network, right? So can you tell me quality factor in terms of R, L, and C?
1 by r into root LC.
Is it? Just how you derive, tell me. So quality factor as a function of R, L, and C, you tell me. Because you know it is now omega naught L by R or 1 by omega naught R into C or VL by VR or VL by V supply or VC by VR or VC by V supply, mod of it actually, everything. So now from this, can you tell me quality factor as a function of R, L, and C for a series RLC network? Yes, how to derive? Tell me. Omega naught is 1 by root over LC. So plug it in. So Q becomes 1 by root LC into L by R. So 1 by R root L by C. Not root LC, okay? Root L by C. So up to now, you know how to derive the quality factor for any network. You just find the maximum energy dissipated and divided by power at resonance multiplied by omega naught. As per definition, we just derived, right? From this one. That is the way. So we are looking into series RLC networks, which are very popular and common for the questions. So can you tell me the quality factor we termed? So basically, what is quality factor? Quality factor, what interpretation it is giving you? If quality factor is too high, what can you tell? Or too low, what can you tell? What is actually it giving us? Information about network. Some information it is giving, right? What information it is giving? So it has no units, right? It is a factor. So also Q, before talking about that, omega naught L by R was Q. So it is nothing but XL by XR, or AR, sorry, not XR, XL by R, or XC by R of mod. So what can I tell is, this is quality factor, not reactive power. Okay. So what can you tell from here? If I multiply I square, it is nothing but reactive power, Q reactive by P active. And active by P active, it is tan of theta, but theta is power factor. This quality factor is of the network to store the energy versus to dissipate. So if it is too high, what can you tell? Quality factor too high, what can you tell? My screen is visible, right?
Visible, sir. Visible. Visible.
What can I tell? Quality factor, I told you.
Power
If it is
dissipation is
too
less.
high, what can I tell about the network?
Power
Yes,
dissipation.
please be louder. Yes, power dissipation is less, or else the reactive elements are too high. It is highly reactive in nature, right? So what actually you can understand that if I draw the impedance versus omega, your XL is with omega for XL, which is nothing but omega naught into L, or omega into L, and this is XC, 1 by omega C. It is like a hyperbola. So we know XL plus XC phasor wise, okay, will give you X net. So your net impedance will look like actually this. That at very less frequency, your capacitive will dominate. So this part becomes capacitive, and this part becomes inductive. So if you operate at high omegas, your circuit will go to lagging circuits. Otherwise, lower omegas, it will be as leading. And that minimum impedance it will offer, you know, is R, because R plus J XL minus XC. Difference of the two. So if it is 0, impedance is Z, right? So Z mean is R. Why? Because XL and XC are both positive numbers, right? Can never be negative. XL and XC are both positive numbers. Okay. However, due to phase reversal, they cancel each other out in contributing to the net impedance magnitude. But amplitude wise, they are all positive numbers, right? So this will actually minimize the impedance and the current will be maximum. So I versus omega, like this. Okay. Yes, which part you want re-explanation? Can you please unmute and tell me?
Sir, the graph.
So what is the graph telling? Graph is telling what is Z net. We are telling about Z net, right? This is Z net. Z net is nothing but XL plus XC. Right? Phasor wise, I am telling. So if you merge these two, one is this, which is the inductive reactance. So inductive reactance will keep on increasing with omega. And the capacitive reactance will be higher for lower omegas and lower for higher omegas. Because
J XL minus XC.
correct. So what I am telling, XL is omega naught L and XC is 1 by omega naught C, right? So first I drew XL and XC. Understood?
Yes.
So XL minus XC, if you draw and take the mod, but I am writing XL plus XC. Why? Because I came out the same, right? Is XL is J omega L, right? And XC is minus J by omega. The amplitude actually negates omega L minus 1. But I am drawing separate. Okay. See, if two phasors, one is upward, you add the two phasors, magnitude cancelling, right? So that's why phasor always gets added, but the phase actually decides whether your amplitude will add or amplitude will reduce. So maybe I think the slide is lagging for some reason. Can you see the slide?
Completely visible.
Okay. Just let me just. I think now
I read visible.
Uh,
Yes, sir. But why is
so what I am
little
trying
bit
to tell
disturbing,
is,
sir?
just let me once. Fine. Am I audible? Hello?
Sir,
Yes,
you are
sir.
audible.
Now what I am telling, see. So where were we? We were discussing about this. So there was a confusion in drawing the waveform, right? See, what was your XL? XL is like this, magnitude wise I am telling, right? It was omega naught L. Just concentrate on the magnitude, okay? It was omega naught L. And XC, mod of XC, what was it? 1 by omega naught C. But we know that X net is nothing but mod of XL minus mod of XC. Actually not minus, it is difference between the two. Because if XL is more and XC is less, it is on top. If XL is less and XC is more, then it is down. So it is difference of the two, because ultimately amplitude wise it will be a positive number only, right? But the phase will decide whether to pull it down or pull it up. So what I am telling, if I ask you what is the amplitude, okay, at low frequency, obviously this will win, right? This will win the race because it is J omega naught L. But here we are only bothered about the magnitude because this will be too low. So at low frequency XC will win the race, right?
It's dominating, sir.
Yes, XC will dominate. at low omega. So this will be in the race. But x net will be difference of the two. So, but this is 0, right? This is, if you negate or add, this will be same. So this is 0, this is this. So it will be like this. And this will dominate. You can just neglect this part. Because this is very low, right? And this is very high. So if you negate XL minus XC or XC minus XL, whatever you do, that in the two difference, what is it? Capacitor will be in the race in speaking in terms of magnitude, because we are drawing mod Z. Okay. So what is it? Mod of XL minus XC. So in mod, either you do XC minus XL or XL minus XC. It is same. So this is X net mod. So this will be in the race. So I am drawing mod Z versus omega. And then mod XL will be in the race at high frequency. So it is like this. But it will be not linear, because there is a hyperbolic addition or subtraction. So what will happen? It will be higher, but the curve will be like this. But this will be in the race. XL at high frequency. And this minimum impedance occurs at omega. The current, then how it will look like? It is V by Z. So current waveform will be mod I, mod V by mod Z. It will be inverted of that, right? V by R. That is what I am trying to tell. Obviously, it will X net is XL minus XC. Agreed with you. So you get the two curves XC who is winning the race, and then minus XL. But that negation will not cause much harm, because this is very small and this is very large. So waveform will follow this one. Obviously, its value will reduce little bit, but the waveform nature will be like this. So it is clear?
Yes, sir.
So now what we are
Yes,
trying to understand is that, see, we understood that X net is XL minus XC. Why? Because of the opposition in phase. This is XL and this is XC. Now whoever wins the race based on omega. Whoever wins the race will go and contribute to reactance. But what happens in resonance? The network does not see any reactance. So at resonance, network reactance is zero. Net reactance is because imaginary part of Z is completely zero. What Z? Z seen by supply. Please be careful. Z seen by supply. This is no other Z, but Z seen by supply at resonance across the ports of the supply. When you calculate the effective Z effective, then we are talking about this Z effective and imaginary part of this Z to be zero. If you equate, then you will find omega naught, resonant frequency. Please be careful about these steps. We are not talking about any Z, but only a particular Z supply. Supply virtually sees the impedance, and in resonance it does not see any reactance. So imagine across the impedance, that is across the supply, should be zero. Right? Slide moving or not?
Slide not moving, sir.
Oh, this problem is not getting over, right?
Now,
Yes, I understand. Now it is moving. Maybe because of the video, I'm turning off the video, right?
బొండాలు ఉంటాయి కదా అలా బయట టిఫిన్ షాప్ లో అలాంటి ఫోన్ లో చూసా. యూస్ చేస్తాను. ఓకేనా? ఇంకా
So hope you understand this, right? Please let me know.
Now, okay, sir.
Okay. So can you calculate the energy? So V is V cos omega t, right? This is R, this is L, this is C. Yes, please tell me. You can see, right?
At resonance condition, sir. Energy at a resonance condition.
Total energy at resonance, maybe. Because now I can freeze the forcing frequency to be at resonance frequency.
I square RT, sir.
No, calculate the total energy stored, right? Why you are only taking the resonance, the resistance. Take the inductor, take the capacitor and try to find out the net. And I am telling energy stored, okay? This is energy dissipated.
Yes, sir.
I am asking you energy stored by L and C. Who will store? Obviously, the reactive elements will store. And who will dissipate? The resistance will dissipate. But I am actually at resonance stored, okay? Try calculate. Right. So at resonance, okay?
Sir, at resonance condition, both the L and C are short circuited.
Yes, but that is only for simplification of the network, right? But they are not gone, actually. Their effect seems to nullify, and the voltage, sum of voltage across L and C is 0, but individually voltage across L and C are not 0. Is it clear?
Yes, sir. Clear, sir.
Why we shorted? Because to simplify the other part of the network. But L and C are not gone. Their voltage across individual L and C, net voltage across L and C sums up to be 0. That's why we replaced it with a short to find out the current. But L and C are not going anywhere, right? L and C are there. They have individual voltage drop across them also. Just I showed you. But what happens? The voltage drop across L and C cancel each other. That's why we shorted. But if I ask you, are they storing energy? Yes. But what is happening at resonance? The part of energy stored by the inductor is equaling with the part of energy released by the capacitor. So there is an energy exchange matching at resonance. That's why they can be replaced and their effect can be nullified. Okay, how much ever L is storing, capacitor is delivering that. So effectively it is not taking or giving anything to the supply. So in reference to the supply, I can nullify their effect, but they are not gone anywhere because they have individual voltage drop across them. Hope it's clear, right? So on the frame of reference of the supply, L and C are gone and can be replaced for a series RLC with short. But individually L and C are there, sitting there, and they are exchanging the energy with them. That's why their effect seems to be nullified in part of the supply. But L and C are storing and releasing energy. Whenever L is storing, capacitor is delivering. Whenever L is delivering, capacitor is storing at resonance frequency. It matches. That's why the term we can replace them by short for a series RLC holds true. But they are not gone anywhere. Okay. So now that's why I asked you to calculate the total energy stored in the resonance process. And I want to show you something. Okay. So quickly calculate. Okay. After this, you will be able to solve all the problems. We'll just see parallel RLC and the quality factor. So quickly do it. I'll give you 1 minute. And then E total stored. Okay. E total stored at resonance. Tell me what I can write. Basically, you can write EL plus EC because you still don't know what is happening. Now, what is EL plus EC? Energy. Tell me. I, you know, right? At resonance. All at resonance, I am asking.
At resonance.
So now you know it is V by R because the effect of L and C seems to nullify. So like likewise, you can write Vm cos omega t. And L you can write half L I square. Now at resonance, it will be half into L into Vm by R whole square cos square omega t. Because I is nothing but Vm cos omega t. So Vm square by R square cos square omega t. Simply write. Okay. As a function of time. Because they are time varying function, right? And EC, can you tell me?
Half into C square.
C into VC square. Now, how to calculate VC? You know, Q equal to CV. So, I equal to C dV dt. But what CV dV dt? VC dt. I equal to C VC dt. What is VC? Voltage across capacitor. So, don't miss, okay? It is not V supply, but V capacitor. IC, I through capacitor is nothing but C dVC dt. But this is a series RLC circuit. So current is same for through all the elements. But I want VC, voltage across capacitor. So what is it? It is 1 by C integral IC dt.
1 by C into integral of IC into dt.
But IC is nothing but I. And I is nothing but
Max.
Vm by max not. I am just as a function of time I am asking. Not max. Max at quality factor. Okay. Just as a function of time I am wanting to ask you. So 0 to t Vm cos omega t integral of that. Okay. So it will be, if you integrate 1 by C Vm by R, you can just take outside into 1 by omega because of this omega into sine of omega t. So this is VC, right? But what is EC? Energy stored. It is nothing but EC is nothing but half into C into VC square. Now what is VC? Vm by RC omega naught into sine omega t. Hope it is clear. Whole square. This is VC, right? Now EL I told you, EL is how much? Half L Vm by R whole square into cos square omega t. But omega not t because at resonance I am asking. So this omega not. Clear? Do with me how it is boiling down to. Do the calculation. So C into Vm square by R square C square omega naught square into sine square omega naught t. This is EC. Now I have EC and EL. So sum them, what is coming? EC as a function of t and EL as a function of t is nothing but E stored
Both
net
added.
at resonance as a function of t. Reso means resonance, okay. So E net stored as a function of t at resonance. What is it becoming? half into C into Vm by RC omega naught, Vm square by R square C square omega naught square, sine square omega naught t plus half into L Vm square by R square cos square omega naught t. Now can you simplify these two parameters? Yes. Please simplify these two parameters. What is coming? What can you boil it down to? This part. Omega naught square is 1 by LC.
Yes, sir.
Replace. What is coming? So take LC on the top, right? So C Vm square by R square C square into LC. So C cancels, one on this and then one on this. So it is the boiling down to Vm square L by R square. Same as this factor, right? So take half Vm square L by R square common because it is common for all. Then you have sine square omega naught t plus cos square omega naught t. So from this you can also infer one more thing, that you see this sine and cos, right? So what was it happening? When it was delivering, it was taking, right? Hope it is clear what I am trying to tell, right?
Clear, sir.
So because why? Because sine square curve will be like this, right? And cos square curve will be like this. How will be cos square curve? Like this only, right? Let me draw it clearly.
Inverse,
What I'm trying to show you is when the inductor was releasing energy, the capacitor was taking that energy and same amount of energy. And when the capacitor was trying to deliver the energy, at that moment, at resonant frequency, inductor was accepting same amount of energy. Only there is exchange. When it was trying to deliver, it was trying to accept. That's why their effect nullifies. What I was telling you from the beginning, that this happens only at resonant frequency. Because only at resonant frequency, this factor equal to this factor, right? Hope you understand.
got it.
And sine square and cos square are here negating each other. That is when it is giving, it is taking. Why it is so, I am trying to tell you, is because there is a 180-degree phase reversal happening, right? So this sums up to be, if you just do and just check sine square and cos square curve, how it looks, you will understand, okay? So I'm talking about the net energy delivered and exchanged over one cycle, right? So you can see that at one cycle, how much ever inductor tried to give, capacitor accepted that energy. It may not be instantaneously reversed, but you can see that over a cycle, how much ever inductor tried to deliver, that much the capacitor tried to accept at that time, right? So just check and you will understand, right? So what is E net? Half, this is 1, right? Half Vm square L by R square. And what is Vm square by R square? Im square. So half L Im square or half C Vm square. You can just derive from here, okay? So E net is nothing but half C Vm square or half L Im square. Just for your reference, okay? Yes. So, and also one more thing, energy stored is independent of frequency, right? Independent of.
So the last line is
Yes, please be loud.
the last line half Im square L, then
Im square L into half. half L Im square. We derived it, right? Because sine square omega
Yes.
t plus cos square omega naught t is 1, you know. And these two factor equalizes only at resonant frequency. That's why we took common Vm square L by R square, and then this term is 1. So what is E net? E net is half into Vm square by R square. Vm square by R square is nothing but I. I am at resonance, right? And then it is L, or half C Vm square. Both you can write, because you know that omega naught is 1 by LC. Omega naught square is 1 by LC. So now you know that also that VL is nothing but Q times VR. I told you at the very beginning, we derived also. And Q at V resonance. Because V supply, right? All are same at resonance. Because at resonance, the L and C can be shorted only for a series RLC. And the voltage supply voltage matches the voltage drop across R. Because VL plus VC in phasor terms is 0. But they are not gone anywhere, okay? With respect to supply, we can short L and C. But they still exchange energy with themselves, right? But not with supply. So to supply, they are not there. It seems they are not there, right? That's why we can short it with a wire for a series connection. Hope it is clear, right? So for Q greater than 1, there you can also infer that the voltage drop across inductor and capacitor are greater than the supply voltage, but they cancel out to be 0. So to the supply, the inductor and capacitor are not there. They behave just as like a short circuit, only for a series RLC, because the sum of the voltage drop across the inductor and capacitor are 0. Can you just tell me whether it is clear to you all? Because it helps in problem solving, this concept, right? For a series RLC, completely stressing upon the terms. For a series RLC circuit, this holds true. Because for other circuits, this does not hold true, because the term resonance means what? That the network is free of any reactive elements. It seems to the supply that the network is free of any reactive elements. Now for a parallel network, it seems to the network that it is free of RLC elements, means it will not draw any current. So to model no current, you can replace it with open circuit. That's why the term open circuit and short circuit are only valid in their respective configurations. But the definition of resonance still remains true, that the imaginary part of Z is 0 at resonance frequency. Because they are exchanging energy with themselves only, not with the supply. So with respect to the supply, it seems that they are not there. That up to that much it is true, but how to model that in series or parallel, that those two are different approaches. So up to this we are seeing for the series RLC circuits, right? Up to this all are clear, right? And Q is also, I told you, omega naught L by R, all those things, okay? And then XL by R or XC by R, all mod. These things are all clear, right? We derived also many times. And also reactive power by, right? P active.
1 by R.
Active.
All those things true. Okay, all those things true. Got it, right? So series RLC, I think it is clear. Now tell me for one more thing, for a coil, how to derive the for coils? For coils, your Q is omega naught L by R. Simply because as per the same definition, right? And Q
Sir.
is 1 by omega CR. Yes.
Sir. So Q equal to reactive by active power, sir. One more formula.
Yes, but that is only true if you have connected a source. Okay. If there is no source, like this, you know, only a coil, then you can see by injecting a test source and a test current, and then you will find out that it comes out same, omega into L by R. Omega means the excitation frequency. Okay. Omega means the source frequency. Omega L by R, and 1 by omega into R. Omega into R into C. Okay. Same as we have derived. Now you tell me for a parallel RLC circuit, right? For parallel RLC circuit, before that we can also drive into the concept of bandwidth, right? Small concept. What is bandwidth?
F2 minus F1.
No, your Z is a function of omega, as you can understand. So Z may be a function of omega and look like this, or somewhat. Okay. I also, I can write I as a function of omega. I is also a function of omega, right? Z and I all are function of omega. So wherever your current is 1 by root 2 times of the actual current at resonance, then you can, or the maximum current, because the resonance current is the maximum current. That's why I'm telling I max. And this is 1 by root 2 times I max. Then at those frequencies, that range of frequencies, we can term as bandwidth. So writing it, bandwidth, I can write the definition is the range of frequencies for which is actually the del of the range of frequencies, the difference. Okay. F2 and F1, the difference. Okay. Is a range, the difference of the range of frequencies for which your voltage, current, gain, either voltage or current. Okay. For a parallel circuit, it will be current, and then for a voltage, okay, gain is 1 by root 2 times maximum. Why 1 by root 2 times, you know? Because, see, if you convert this gain or amplitude to decibels, then what will it be? 20 log 10 into gain equal to gain in dB.
Yes.
Then if I can write 20, why this root 2, you see, 20 log 10, 1 by root 2 is there, right? So that means it is coming minus 3 dB. Let's confirm whether it is coming minus 3 dB. 20 into log 1 by root 2. Yes, it is around minus 3 dB, right? So why is this 3 dB gain important? Because at this gain, the power becomes half. Why? Power is I max square R at that point. If I try I by root 2, then what is power? Whatever, RMS or peak, leave it. If that overall is 1 by root 2, then power becomes P max, becomes P max new, if I can write, is half of P max old, because 1 by root 2 square becomes 1 by 2. So this is also known as half power frequency, because at these two frequencies, these are both half power frequencies, because at these frequencies, the power becomes half, because the current depends on frequency. And at this frequency, current is 1 by root 2 times. So power at that frequency is 1 by root 2 times. That's why half power frequencies. And if you can find the difference of the two ranges of frequencies, that is termed as the bandwidth. So bandwidth is nothing but the difference of the half power frequencies. Two half power frequencies.
So that's why 1 by 2 are there.
Yes, 1 by root 2 square. Okay. Plug it in, you will get half of P max old. P max was I max square R. Now I max by root 2 square R, if you do half I max square R, and half I max square R is nothing but P max old. So half the previous power, because there is a square, right? So half power frequency, that's why. At these two frequencies, since the current is 1 by root 2 times, that's why the power becomes half of the old. Hope the concept is clear, right? But you need to know more. See, so bandwidth you understand now, that it is the half power frequency, right? But there are some small derivations that at bandwidth, see, I at resonance is V by R for a series RLC network, right? This much is clear. V means V as a phasor form, V by R. There Z was R at resonance. Or you can write. So XL minus XC was 0 at resonance, right? So power factor at resonance, as per the impedance triangle, X net is 0. This is R, this is Z. So Z is R, because this square plus this square is Z whole root over. But what is cos theta? Cos theta is base by hypotenuse. So base by hypotenuse. But this is R square plus XL minus XC whole square. But this is 0, X net. So it is nothing but 1, because this height is 0. So R matches Z. So R equal to Z. So cos theta was 1, right? How much is theta? 0 degree at resonance. Now, circuit is at resonance only, but think that I is now I by root 2. Then what will happen? Virtually, then Z behaves to be as root 2 times R. Is this clear or not? If I equal to I by root 2, I new equal to I old by root 2, and V by Z equal to I. If I is 1 by root 2 times, that means Z becomes 1 by root 2 times, because V is fixed. So Z is now thought to be 1 by root 2 of Z old. And what is Z old? R. Sorry, root 2 times, not 1 by root 2. Z is root 2 times Z old. So Z now new is root 2 R. Because only if Z is root 2 times R, I will be 1 by root. Because we want to find half power frequency, okay? That omega 1 and omega 2. I told you na, that half power. So current is 1 by root 2. To make current 1 by root 2 at resonance, R should be, or Z should be root 2 times R. This is at resonance. So new Z still should be resistive, but root 2 times, because current is 1 by root 2 times. So impedance should be root 2 times, but resistive. Clear? If Z is root 2 times of old R, then only current should be 1 by root 2 times. So now, if Z is root 2 R, can anyone tell me what is cos theta? Theta new at half power frequency. Cos inverse 1 by root 2 or 45 degree. So power factor at half power frequency is 1 by root 2, right? Because also you can write like this. I can make a new maybe slide and write for you again. At half power frequency, so what happens? Z is root 2R. Because I is I max by root 2. At half power frequency, I am telling. Circuit is still at resonance. because we are talking about maximum, right? So current should be maximum, but 1 by root 2 times at maximum at half power, right? But we know Z is R plus J XL minus XC, and Z is root 2R magnitude wise. So R plus minus JR. If only this is R, then only magnitude is root 2 times. If mod of Z is root 2R, then only this will be happening. This will be R only. So XL minus XC is plus minus R, right? Two cases are coming. And I told you cos phi is R by Z, R by root 2R, and then phi nu at half power frequency, okay? This will be 1 by root 2 cos of that. So phi nu is nothing but 45 degree, plus minus 45 degree, right? Or cos theta, cos phi nu is nothing but 0.707. Hope it is clear. It is only the analysis what will happen at half power frequency. The current is like this, so the power factor will be like this. Because you know the R is still there, but the Z is root 2 times R magnitude wise. That's why it is happening. Yes, so two more things. From here we can calculate actually omega 1 and omega 2. Just calculate. One more slide I can give. So what is happening at low frequency, at the lower frequency, which is omega 1. So there are two frequencies, right? I is like this is I by root 2, this is I max. So this is omega 1, this is omega 2. We are trying to find both these half power frequencies. These are all half power frequencies. So how to find out? We know one parameter that you're from this one, XL minus XC is plus minus R. Up to this we know, right? So I told you at lower frequency who will win, because this is omega naught, right? At resonant frequency, the current is maximum. This is omega naught. This is omega 1, this is omega 2. So this is resonant frequency. So who will win at omega 1, which is less than omega naught? So at lower frequencies, who will win? Capacitive reactance or inductive reactance? Capacitive, right? XC wins XL. So XC is greater than XL magnitude wise at omega less than omega naught, or omega 1 which is less than omega naught. Up to this it is clear, right? So XL minus XC will be negative, right? And XL minus XC can be minus R. But at omega greater than omega naught, or omega 2 which is greater than omega naught, XL minus XC will be plus R. Because we got two results from here. In order for Z mod to be root 2R, either it can be plus R or minus R. Because XL offers positive plus J. So XL minus XC we write, right? Plus J. This is impedance. Now who will win out of two? We told that the amplitude wise capacitive reactance will be more at lower frequencies. So if so, XL minus XC will be negative at lower frequencies. And that will match with the sign minus R. And this will be plus R. So you just do and you will find out that what will be the omega 1. So this is new frequency, right? At half power frequency, omega 1 L minus 1 by omega 1 C equal to minus R. And one more equation will be omega 2L minus 1 by omega 2C equal to plus R. And omega 1 and omega 2 you can find from here. So I will write, you just solve a quadratic equation, both, and you know omega 1 and omega 2 are positive numbers and eliminate the negative one, and you will get omega 1 to be minus r by 2l plus root over r square by 4l square plus 1 by lc, and omega 2 to be what? R by 2l plus root over r square by 4l square 1 by lc. So omega 1 and omega 2 you can get, and just you can get a result that omega 2 is greater than omega 1 for sure. You can see in the image also. So omega 2 is greater than omega 1, not greater than omega 1, right? And omega 2 minus omega 1 is nothing but bandwidth, which is nothing but from here you can just calculate, it is coming r by l. So bandwidth is nothing but r by l. And if you see also one more relation, bandwidth is omega naught by quality factor. Because what was quality factor? Omega naught L by R. Then if bandwidth is R by L, you multiply omega naught on top and bottom. Then you will get bandwidth is quality factor by omega naught. Sorry. Yes. 1 by
Omega naught by quality factor.
bandwidth is 1 by quality factor into omega naught. This. What you are telling? Please let me know.
Sir, I am telling this. Omega naught
Huh?
is by Q.
Omega naught is, please be loud.
Bandwidth is equal to omega naught by Q.
Correct. By Q, I told you, na? You just multiply omega naught. See, we are getting bandwidth is R by L simply from these two roots. Omega naught, omega 2 minus omega 1 is nothing but bandwidth. I told you this. See this diagram. Omega 2 minus omega 1, the difference of the half power frequencies will give you bandwidth. Now bandwidth we are getting R by L simply. Now I multiplied omega naught top and bottom. What it comes? Omega naught R by omega naught L. Now you know omega naught L by R is Q. So omega naught by Q. Bandwidth is omega naught by Q. Okay. And bandwidth unit is radian per second. Okay. Because it is frequency only. Difference of two frequencies. Bandwidth is simply difference of two half power frequencies. In the diagram also you can see. And there is a term there called selectivity, which is proportional to 1 by bandwidth.
The radian per second unit.
Second unit what? Quality factor. Quality
Radian
factor
per
has no
second.
unit.
No, sir. Bandwidth unit is radian per second.
Radian per second or hertz. If you take these to be angular frequency, then your bandwidth difference will come in radian per second. Also, sometimes they tell in hertz also. Because all are frequency, right? You tell radian per second or hertz, 2 pi factor will be there. Okay. If you want in radian per second. They are all frequencies, simply. So what I want to tell you is that bandwidth, which is nothing but f2 minus f1, is nothing but f naught by q, or omega 2 minus omega 1 equal to omega naught by q, right? Quality factor. So what is happening if the quality factor is too high, right? If the quality factor is too high, bandwidth is low. That means quality factor gives you sharpness of I waveform. The current waveform. See, the current waveform, it is too sharp. Then at half power, that bandwidth will reduce, right? This bandwidth was for the sharper waveform, and for the less sharper waveform, you see bandwidth was more.
So the quality factor is high or low?
High for the sharper waveform. If the waveform is sharper, it accommodates lower bandwidth, because bandwidth is nothing but omega naught by q. Q denotes the sharpness of the waveform. So if q is high, bandwidth is low. Just I showed you by drawing also that if you have a waveform like this and a waveform like this, 1 by 2 times of this waveform will give you this, but 1 by 2 of this lower waveform is much broader. So the selectivity is nothing but capability of the waveform or the capability of the system to catch more or catch a particular frequency within the bandwidth. So obviously, if bandwidth is low, the selectivity will enhance. and the bandwidth is inversely proportional to quality factor. That means as the waveform is sharper, its quality factor will be higher and it will accommodate lower bandwidth. But lower bandwidth signals are better in a sense they accommodate the lesser noise. Bandwidth is small, means noise frequencies, other frequencies are attenuated well. So we say the system is well selective, very selective. It is good for particular small bandwidth, but selective. That is, it is less noisy, right? Selectivity high means less noisy. So in communication, these things are very much used. They are using specific spectrum of frequency, mobile also.
Selectivity less means?
Selectivity less means what? Your bandwidth is more, you are accommodating more noise. So that's why they are inversely proportional. Bandwidth and selectivity are inversely proportional. And quality factor and selectivity are directly proportional, as you can see. So these are used in communications, right? Communications. So I just thought to explain this term so that you can connect. Okay. Otherwise, it is okay. Other things I told you already. And sometimes you can approximate also, that for very approximate calculations, but I will prefer tell you not to use it, but you can use omega naught plus, you can use bandwidth by 2, because this is symmetric, right? So omega naught, this is omega naught in the center plus bandwidth by 2 will approximately give you omega 1, and omega 2 approximately is minus, and omega 2 is omega naught plus bandwidth by 2. These are crude results, approximate results, right? But I prefer to use these two results, that omega 1 and omega 2. They're actual
Minus.
bandwidth, yes. See, these are symmetric. Current becomes maximum at resonant frequency, and at half power frequency, these are omega 1 and omega 2. This is bandwidth. So I just crudely wrote that omega 1 is nothing but omega naught minus bandwidth by 2 because of the symmetry. This is omega naught plus bandwidth by 2. But these are crude results. Actual results are these. Minus plus how? Omega naught is in the between. This is the bandwidth. So bandwidth by 2 is this much distance. Bandwidth by 2 is this much distance. So omega naught minus bandwidth by 2, you come to omega 1, which is smaller than omega naught. And omega 2 plus, omega 2 is what? Omega naught plus bandwidth by 2. This small distance is bandwidth by 2. I'm approximating, but this depends on the quality factor. This is not a linear relationship. This is approximately linear relationship. But as you can understand, this also depends upon the quality factor, which are R, L, and C elements. Okay. So this holds for if nothing is given, and if they simply ask you to find out the half power frequency and you know the resonant frequency, then you can do this. But if you know RL and C, if you know RL and C already, and you know the resonant frequency, then I prefer you use this formula. Hope you understand what I'm trying to tell. These are approximate formulas, and these are approximate formulas, and these are direct formulas. Okay. So this formula and this formula are direct formulas.
Exact formulas.
Exact formulas, yes. And this is approx formula. I can write in another color. This is approx, okay. So now we come to the, before this the problem, simple problem. I will just take 15 more minutes, right? So I am talking about the parallel RLC resonance, which is a very small topic if you understand the series RLC resonance. So parallel RLC resonance, series RLC resonance, fundamentally no difference. To the source, the network behaves to be completely resistive. So just finding, yes. Okay, one more thing, small thing I can just cover before the parallel RLC, because it will be important. If you know, it will be better. There is another term, damping ratio, right? and it has relation with quality factor Q. So we were talking about RLC. And if this is V naught,
Sir, this is also Q.
Q, quality factor. No, damping ratio is D or zeta. Damping ratio is denoted as zeta. And it has relation with quality factor. Let me not write here, otherwise you will think both are same. Zeta is related somehow to quality factor. Obviously, that R, L, and C element strengths determine the damping ratio. And also the RL and C strengths determine the omega naught. Also the RL and C magnitudes determine quality factor. All are decided by RL and C values, as you can understand. Quality factor also determined by RL and C. Zeta also denoted by RL and C. So all are related. How related? If you draw the transfer function of the Vi and Vs, it will come. You draw it. SL and 1 by CS. You know, na? So V0 by Vin, when you do, you will get omega n square divided by SL plus 2 zeta omega ns plus omega n square. Omega n is what? You will get it, okay? Where you will actually get this formula. V0 S by VIS. If you do V0 S by VIS, you will get 1 by LC by S square plus R by LS plus 1 by LC. Now, if you compare, this is a standard second order system, right? Where zeta is the damping ratio and omega n is the natural frequency. If you compare, you get 2 zeta omega n as R by L. And what was R by L? Bandwidth. Get it? R by L was bandwidth, okay? By comparing. And omega n was the natural frequency. It was what? 1 by root LC. Same as resonant frequency. So now if you see, zeta is coming from this relation. What was zeta coming? R by 2L into omega n. 1 by root LC. Sorry, 1 by root LC, okay? So R by 2 root 1 by root LC into omega n. So root LC goes above. Omega n is there, na, what I am writing. You do this, what is coming? R by 2 into L omega n, right? Omega n is 1 by root LC. So what it is coming? R by 2 root C over L. So zeta is nothing but R by 2 root C over L. And your quality factor is what? 1 by R root L by C for a series RL circuit. Also 2 zeta omega n is bandwidth. So from these two, you get zeta is 1 by 2 times quality factor. 1 by 2 Q. Clear? So this is the bandwidth, right? Yes, clear or not? Please tell me.
Clear,
So
sir.
This is how zeta, the damping ratio, is related to your quality factor. And you know, if damping ratio is 1, we say the network to be critically damped. If zeta is greater than 1, that means if this zeta is greater than 1, what it means is that, yes, if R equal to 2 root LC, then your zeta equal to 1. This means it is critically damped. You just check, okay, zeta will be 1. Then only R equal to 2 root LC. Then if R greater than 2 root L by C, then for this zeta is greater than 1. And then it is over damped. And if R less than 2 root L by C, then what it is? It is underdamped. For underdamped, you have oscillatory response like this. For critically damped, you have something like this response. This is YT, the response. And this is time. I am doing the time domain response. And it is further sluggish for overdamped. This is underdamped. And this is critically damped. For underdamped, you know it is the system has complex conjugate pair of poles. Because you can just draw the roots of this second order system and understand. For complex conjugate pair of roots, obviously zeta is less than 1. And if zeta is greater than 1 or equal to 1, the roots are real. So you get either critically damped response or you have overdamped response. So that is what I just wanted to cover. And coming to the problems, before problems, parallel RLC, I just want to explain, and then you will come to one problem. We just solve one problem and you will get complete scenario of what happened till then. Okay, so we'll just solve one problem and then I'll solve two concepts of three phase. Okay, so 15 more minutes. So parallel RLC, right? Parallel RLC. So parallel RLC just same. The network will look like this. Just 1 second. Yes. So parallel RLC.
Connected.
What you are telling?
Network is parallelly connected.
Yes, yes. Just simple. Either connect a voltage or a current source, doesn't matter. So this is some inductor and this is some capacitor. Now I told you for parallel, dealing with admittances are easier. So I draw the, instead of R I write G, which is 1 by inverse of Y is nothing but inverse of
parallel.
Admittances are easier to deal with, right? Because you have the voltage drop summing up in the series circuit, so you draw with impedances. Now you draw with admittances because V equal to IZ or V into Y equal to I, and you just multiply V into Y for this branch, V into Y for this branch, V into Y for this branch to get the current of this branch, current of this branch, current of this branch. That's why dealing with impedances are easier. Sorry, admittances are easier for parallel RL circuit because current sums up. And in series RL circuit, the voltage sums up. That's why dealing with impedances are easier because this one. So take in form of voltage in series, take in form of current for parallel. And to draw everything in terms of current, you have to deal with Y. Y is 1 by Z. But R is not 1 by G and B is not 1 by X. Clear about this? R is not 1 by G, right? G is nothing but real part of Y. B is nothing but real part of Y. Sorry, imaginary part of Y. R is nothing but real part of Z and X is nothing but real imaginary part of Z. So they have no correlation as inverses. But Y and Z are inversely related. Okay. Y equal to 1 by Z or Z equal to 1 by Y. Now once you do Y, you take the real and imaginary, you find G and B, which is nothing but conductance and susceptance, right? Clear? Clear or not? Y and Z are inversely related, but R and B and G and X have no relation. No relation, right? B is susceptance. This is reactance. G is conductance, right? R is resistance. Hope you are clear with these things. I am continuously repeating for your benefit, right? So that you are not in a misconception that, okay, R and G are somehow related. No, nowhere related. You take Y, take the real part, you get the G. Take Y, take the imaginary part, get the B. Dealing with G and all those things are easier. So it is minus JBL and minus and plus JBC. Why? Because you know that your XC is minus J by omega C. So 1 by XC you do. Why? Because this branch only has capacitance. So 1 by XC will be nothing but BC. And this is J omega C. or in other words, J B of C, small c. Because B of C is nothing but omega c. For a shunt branch, because shunt path has nothing else, right? So 1 by that thing works. And similarly, B of L is nothing but omega L. 1 by omega L, okay? BL is 1 by omega L, BC is omega c. And G is 1 by R. This is working one only because these branches don't have any other elements. But in general sense, R and G are not inversely related. For other network, like this R and then there is L in same branch, then you cannot write that, right? There is simply R in this branch. So I can write conductance for this branch to be 1 by R. This is equal to G. Hope it is clear, right? Similarly for L, I can write omega L is at the XL, or BL, that is the susceptance, is 1 by omega L, or J omega L was XL and 1 minus J by omega L, or minus J BL. BL I am terming the coinage as the terms. Otherwise, plus and minus I am actually giving differently. So just at resonance, at resonance, imaginary part of Y is 0. Similarly, imaginary part of Z also you can write as 0, because at resonance, network becomes as free of L and C, or reactive elements. So what becomes, BL and BC are cancelling each other. So BL equal to BC. And BL, I told you BL is 1 by omega L and BC is omega C. Other way around, if you do, you will get XL equal to XC. Everything is similar, okay? So if they are cancelling each other,
So
then
G equal to 1 by R.
What you are telling?
G equal to 1 by R.
Yes, why G equal to 1 by R, I told you, only resistance is there. So what is Z? Z is R. Right? Yes or no? For this branch. So 1 by Z
Yes.
is Y, is 1 by R. And real part of Y is nothing but G, is nothing but 1 by R. But if there were some other elements in this branch, then this would have not hold true. That's why I keep on stressing upon the fact that don't just smug up that, okay, resistance is 1 by G and then susceptance is 1 by X. They are not true if there are other elements with R, L and C in the same branch. Here only because for this branch, I know the impedance is nothing but R. Z is R, right? Because there is no X in this branch. That's why 1 by R is G holds true for this branch. Similarly for this branch, we are doing separately, right? Calculating the admittances for separate branches separately.
G1, G2, sir.
Yes. We are determining the Y's separately for the branches, so that we can find the currents separately for this branch. How much the current? Voltage times Y for that branch gives us the current of that branch. Hope you understand. Now these two currents will sum up to be 0. Similarly, as the voltages sum up to be 0 for the series RLC network, and their behavior was simply like a R resistive. Similarly, here also the currents will sum up to be 0. So just writing it for you, one term, that for series RLC, ALC short behavior, right? And for parallel RC, RLC, ALC together behaves as open circuit. Why open circuit? Because IL plus IC becomes 0. So how to model
No, open circuit current is 0, sir.
how to model 0 current? By open circuit. So just like we do it short for series, for parallel, our L and C path will together behave as open circuit because they are not drawing any current from the supply. For that behavior, in order to model a 0 current, for that those two branches taken together, we just open them. So LC not there, not connected to the network. So it simply boils down to a current source or a voltage source, whatever you want to plug in, but the current going to that lumped branch consisting of L and C is 0. So there is no connection. We can open circuit at resonance only. At resonance only, they will offer this kind of behavior. The currents will sum up to be 0 because I into Y L and I into Y C, that is admittance of L and C, these two will cancel each other. Hope you understand. Sorry, V by YL, V into YL. Okay. What is IL? IL is V into YL. IC is V into YC.
Into IC.
V into admittance of that branch is I through that branch. I into admittance of that branch, V into admittance of L, which is nothing but V into BL or V into BC. Just not taking the signs. They will be just, this is BC and this will be BL. BL will be down with a minus sign. So they will cancel each other. V into BC, V into BL. The I's will cancel each other and sum up to be 0. That is the main concept. Okay. So they will just behave like open circuit and just open them and take the response. And to find omega naught for parallel circuits, you can take Z and equate imaginary part 0, or you can just do imaginary part of Y 0. You will get the omega, get omega naught at resonance or resonant frequency, right? Omega naught means resonant frequency. So by doing this, you get the, because at resonance, there is no imaginary part. Only the concept is that either you take for Y, take for Z, doesn't matter, because dealing with admittances are easier because they can be summed up easily. So admittance net is nothing but Y1 plus Y2 plus Y3 if Y1, Y2, Y3 parallel. Hope you understand what I am telling, because 1 by Z net is nothing but 1 by Z1 plus 1 by Z2 plus 1 by Z3 for parallel, right? Equivalent parallel I am telling. Find out and then you get imaginary part 0 for the net Y and you find the omega. This is the technique how to do. Now one small problem I do with you. One small problem I am searching. Yes. So one problem I am searching is that one. So you have one R and then you have L and C, and they are asking you many things to calculate. 4 millihenry and then this is 0.1 microfarad and this is 200 volts, right? So quality factor for this circuit is given to be 20. So now they are asking to find out several things. One is the resonant frequency omega naught. Second is the current at resonance. And I at half power. And then bandwidth. 4 is omega 1, omega 2, which are nothing but half power frequencies. And this is nothing but resonant frequency. Okay. So all the things we learned, we'll calculate in only one problem. So omega at which voltage across capacitor is maximum, and 6 is frequency at which voltage across inductor is maximum, and voltage across VL and VC at resonance. I told you, na, voltage across inductor and capacitor sum to be 0 at resonance, but what are their magnitude at resonance? That is to be found out. So can you quickly tell me? These are all simple problems we have already covered. So omega naught is what? 1 by root LC.
50K.
Uh-huh.
50K radians per second. 50,000 radians.
50,000. Correct. So 4 millihenry and 0.1. Yes. Correct. So I naught V by R, right? So what is V? R you just take to be 10, okay? Because you are given quality, right? Q is what?
Okay.
20. Q is what? Omega naught L by R. And it is 20. L you know, omega naught you know. You find out R. R is how much? R is how much? 50,000 into L divided by 20. This is R.
1, sir. R value 1.
Huh? R value
R
10.
equal to 1.
R is 10.
Okay, okay, sir.
R is 10. You just check. So with this,
Yes,
you
10.
can calculate I naught as 200 by 10, which is nothing but how much? 20 amps. This is a peak
Sir,
value,
R
right?
equal to 10. R equal to 10.
Yes. See, this is, if this is RMS, then this is RMS. If this is peak, this is peak. And if this is RMS, you want Imax at resonance, then what is it? 20 root 2. Because generally the RMS voltages are specified. So Imax is 20 root 2. Root 2 times the RMS value. Okay? So this is RMS at resonance. So what is half power? I half is 1 by root 2 I. 1 by root 2 of 20. 1 by root 2 of 20 because RMS half power current. Okay. So just 1 by root 2 times 20, all dealing with the RMS value. So it is coming 14.14 amps. I at half power. Okay, bandwidth is what? I told you bandwidth bandwidth formula is R by L. So 10 into 10 to the power 3 by 4. You see the formula, okay? So 25,000 radians per second. Okay. And omega 1 and omega 2, because here all you can do the approximate, you can do the actual. Do both, you will get around same results. Okay. Omega 1 you will get as 48,750 and omega 2 you will get as 51,250. Either you take that formula, direct exact formula, or you do omega naught plus minus bandwidth by 2. You get almost same for this. Just check, okay? And your omega at which voltage across capacitor and voltage across inductor is maximum. So I told you, right, that voltage across inductor is what? Quality factor times V supply. Factor is quality factor times. Then, but they are asking the omega at which voltage across inductor is max. So what you do, can you tell me? VL and VC are C. So I give you as an exercise to calculate voltage across inductor as a function of omega and voltage across capacitor as a function of omega. You know up to this that it is quality factor times V R. And VR is nothing but V supply. For series RLC. Both for series RLC, okay? Otherwise it is not true. Up to this you know. Now what they are asking? Maximum of the both VL and VC, max for what omega? And also VL and VC at omega naught. That is at resonance frequency. Now VL and VC at omega naught calculation is very easy. What? VL equal to mod VL and VCs both are omega naught into V into quality factor. Both are same. Only with just opposite phases. So is 20 into just 20 to 200.
4,000.
Both same. And should be same at resonance. At resonance, they should be same and opposite.
Both.
And opposite why? To cancel. Because you know I is same for series. So I into j omega L and I into minus j by omega c, and these two are equal for resonance. I hope you understand. So VL and VC equal in amplitude but opposite in phase. But opposite in phase because of plus j and minus j. Hope you understand. Just writing the reason for you to get connected. So they are opposite in phase. Just they cancel out and we can short for a series, right? For a series RLC. Okay. So these are easy. But what is asking? This is a new thing. That VL and VC as a function of omega, you know, up to this. We all know. But for what omega VL is maximum and for what omega VC is maximum? Yes? Any idea? And how to find it out? Any idea? So I will write it down for you how you can actually determine. Otherwise you will not be. You can just see how to determine. So you have to actually derive. You will find the result. And equal to 0, right? So find omega for both. But VL as a function of omega and VC as a function of omega, can you tell me? And then you will differentiate with respect to omega to find out omega at which VL and VC are maximum. So 2 omegas will come. Yes, how to actually you find, you can tell me? Yes? Yes, tell me. So VL is nothing but IXL. I is nothing but V by root over R square plus XL minus XC whole square into XL. Similarly, I by R square, sorry, V by R square plus root over XL minus XC whole square whole root over. This is I, right? Into XC. Because if omega is not omega naught, then this XL minus XC will not be 0. So I have to write it. So V by R square plus XL minus XC whole square whole root over is V by Z times XC times XL. So differentiate this. These are all dependent on omega. So I have to write V into omega L divided by R square plus omega L minus 1 by omega C whole square whole root over. You differentiate with respect to omega. Also you differentiate V into 1 by omega C divided by R square plus omega L minus 1 by omega C whole square whole root over. This is VC as a function of omega and this is VL as a function of omega. Differentiate with respect to omega and equate to 0. You will find omega for which VL max and omega for which VC max. So 2 omegas will come. So I'll write down for you quality factor. These two formulas are there. Okay, that what is the frequency for which VL is maximum and what is the frequency for which VC is maximum. So I'll just write the formulas again for you. Okay. So VC omega at which VC is maximum, okay, is nothing but omega is 1 by root LC into 1 by 2 Q square. So this is less than omega naught actually. And omega at which VL, voltage across capacitor, and voltage across inductor and capacitor. Okay. VL is maximum. You can write it as 1 by root LC whole root over 1 by 2 Q square. Q is nothing but omega naught L by R. Okay. So this is more higher than omega naught. So at higher omega naught, VL is maximum and lower omega naught, lower omega, not omega naught, lower frequency. Lower frequency means less than resonant frequency. VC is max. Because as you can understand at lower frequency, this term is also more. And I into more is approximately more. So VC is getting higher for a lower frequency. The voltage across capacitor becomes maximum in the frequency range for a lower frequency. And what is the value of that frequency? The value of that frequency is this. It is at a lower. Because just like the impedance, we just draw that this is capacitive, right? This zone, and this is inductive. So this capacitive zone has higher value of XC, and this inductive zone has higher value of XL. So the VC is also max in this zone, where this is omega naught, and a particular frequency omega C, let us tell, and this tell us omega L. So this omega C, the VC becomes maximum, and omega L, the VL becomes maximum. This omega C is at a zone lower than omega naught. And then omega L is at a zone higher than omega naught. So now come to the problem. This is lesser than omega naught, okay? Voltage across capacitor is maximum in the capacitive dominative zone. And this voltage across inductor is at a zone where the inductive reactance is maximum. So this answer will come out. The voltage across capacitor is maximum. This is coming out. If you use the formula, the two formula that I gave you. So use these two formula, right? And you will find VC is coming. These two formula. Use these two formula and you get a omega for which voltage across capacitor is maximum, and the answer is coming out as, just let me write it for you. Yes, the frequency for which the voltage across capacitor is maximum is coming out as 49.96 kiloradian per second, because this is lower than omega, and omega naught actually, and this is coming out as 50.03 kiloradian per second. So always remember, voltage across inductor will be maximum at a frequency higher than resonant frequency in the inductive dominative zone for a series RLC. This is for a series RLC, right? And this formula is valid only for series RLC. And also you can understand that the voltage across capacitor is more for a frequency lower than the resonant frequency in the where the capacitive impedance is dominating, or the capacitive reactance is dominating. In that term, that zone actually, the voltage across capacitor is maximum. So similarly, you can find out the same for other different parameter values. So we are already over time, but I want to cover few small concepts for the three-phase AC. So three-phase AC means we are having balanced supply, right? Like this. We do the phasor diagram, and for imagine the single phase AC we talked about and drew the phasor diagram. So there are two more, okay? For three phase, there are actually three phases. So three sources separated apart by 120 degree. So if VR is there for a RYB sequence, you have VB. See, you are sitting here. So R comes, then Y comes, then B comes, anti-clockwise. You are sitting here, rotate the phasor. You will first see R, then you will see Y, then you will see B. So rotation in phasor means
phone charge is that
time, domain, variation in time. So we are rotating in the phasor means you are shifting the phase in time. So they are phase displaced in time by 120 degree. In time. So that is the significance of the phase angle displacement in phasors. They mean the time phase angle differences. So just know that, and you know that how to calculate for a delta or star or balanced RL network, right? So these are Z, Z and Z, and we generally draw the AC supplies like this. Let me name them something. So this is, let's say, R, and let me name them Y and B. Then you connect this Y lead to maybe this, and then B lead to this. So the voltage impressed across one phase, I tell this one phase, this is R, this is Y, and this is B. So this is BR, right? VBR divided by Z. This is nothing but your current. So this is IR. Let me name this as R phase, ZR, ZB, ZY. So ZR is nothing but IR. Same IY is nothing but, if this is IR, this is IY, this is IB. IY is what? VRY by ZY. Just see in per phase basis. IB is VBY divided by ZB. Simple, right? Similarly, if it was a star like this, they will only ask you to calculate currents for balanced networks, right? Similarly, RYB is the neutral point, and this is ZZZ. So what you do? This is VR N, because supply is star connected, right? Always supply is star connected. So these voltages are with respect to ground. If nothing specified, you assume that reference is ground. So VRN minus this is 0, assume minus 0 is nothing but VR by Z. So this is IR. Now here one thing, that line, these are all the line currents we tell. And this is the line current, but this is the phase current. One phase, one particular load we tell as phase. But here you can see one load, phase and line are same. This current is same. So we tell actually that for star, line and phase are same. Phase means one load point, one load where it is connected, right? So these are same. And then we can write I line equal to I phase. But here I line and I phase are different because there is a node coming up. So generally I line and I phase are related as √3 times. So I line by √3 is I phase. So why actually √3 came? If you want to analyze this, IR and IY and IB are 120 degree apart. So if you sum them, IR and IY, if you sum two vectors 120 degree apart, if you do IR square plus IY square plus 2 IR IY cos of 120, you get a minus half. So their amplitudes are same, their magnitudes are same because they are balanced. So x square plus x square minus plus 2 into minus half into x square. So you will get same. So what is cos on 120 degree? Yes. What is cos of 120 degree? So IR and IY and IB, what are they phase displaced by?
-1/2.
So you sum up and tell me what it is coming. I want this current, right? This current, I line I call it. And this current summation will give me this current, I line. But this current is actually, we can understand VRY. So let me draw the phasor diagram, otherwise you will not understand. So VR, VY and VB. And if I write it for you here, maybe for delta I draw. So always draw the phasor diagram, otherwise there will be mistakes actually. So maybe you connect here R, maybe you connect here Y, and maybe you connect here the B. phase points, right? Phase supply points. VR, VY and VBU connected, right? So this current I am actually trying to calculate, and these two currents are there. If I take the direction in this direction and write it as I, maybe some 2, and write it as I1, can anyone help me? What is the value of I1 and I2? It is nothing but I1 should be, this potential should be higher, VR minus VY by Z, and I2 will be VR minus what? VB by Z. So can anyone tell me VR minus VY what it is? VR minus VY means this is minus VY. So add this. So this is
VR
VY and VRB. RB, how it looks? RB. So what is this angle between those two? Because VRY by Z and VRB by Z also, if Z is R for simplicity, then 0 degree phase apart. Then
60
this is I, this is I, this is I1, this is I2. By R, so scale down somewhat. So what is the angle? These two angles. This is C. VB and VR angle was 120 degree. So what is the angle between? Because VB and VY was also 120 degree. And VB and minus VY angle was? This angle was 60 degree because this is 180 degree. So now this angle is 120 degree again. VB and VR. And there is a 60 degree difference. So what is the angle between VY and VR? 120 degree. Sorry, 60 degree, right? This angle. This angle I am taking. This angle is 60 degree. Because this much angle is 60 degree, this much angle is 60 degree. That's how they sum up to be 120 degree. And the bisection point, because this is equal to this, so this vector will be bisecting the angle. You can also check. If two vectors you are adding of same strength, then in the parallelogram, they will just bisect the angle. So this angle is 30 degree.
30 VRY and VR 30, sir.
Both are 30 degree. So what is the difference between the two? This I1 and I2, if I sum up. Two equal currents with 60 degree apart. Then your I, this I, is sum up I1 and I2, and I1 and I2 are 60 degree apart. So x square plus 2 into x into cos of 60 degree. That's why we draw the phasor diagram. Otherwise, it would have been gone wrong. The mod of that. So it will be 3x square, right? Whole root. So you see I line, which I termed as I, the line current is √3 times the phase current, because one phase current amplitude was x. Mod of I1 was equal to mod of I2 was equal to x. I just take one amplitude. So that's why it is √3 times. Similarly holds for voltage, that V line and V phase is nothing but √3. So it is easy, right? Just take care of the phasor diagrams I just showed you. Another concept on just wattmeter. There is a problem of wattmeters, that for a balanced AC system, you need n phase, maybe you need n-1 wattmeters. You don't need n wattmeters. N-1 is sufficient if the system is balanced. So what that means is, if this is R, this is Y, this is B, and you have the load maybe like this, and this is the supply. So what I do is I put wattmeters like this. So I call it W1 and W2, right? So what is W1 and what is W2? The current coil is like this and the pressure coil is between R and Y. Similarly, for the second one, the current coil is in the IY. See, this is IR, this is IY, this is IV. And obviously, this is RY, VRY, and
into
this
I.
is YB. So what is W1? You tell me.
VRY
Into IR.
into IR cos of.
No, just cos Y cos. Just I am
Angle
telling you.
VRY and
I will come. No, I am telling W1 is what? W1 is recording what? VRY and IR. Now what it will come, we'll just see. So recording VRY and IR, right?
Yes, sir.
And W2 is recording VYB and IY. And what is the phase sequence? R, YB. Only holds true. This connection only holds true if the sequence is RYB. Means you are sitting here and this is R, then Y will come, then V. This connection only works and gives you the desired results if the sequence, so desired results for connection, for this connection only if sequence is RYB. Let us see how. The first wattmeter was recording VRY, right? Stay with me and draw the phasor diagram. And the first wattmeter was also recording IR. The second wattmeter was VYB and recording IY. So tell me what is the phasor diagram, okay? For simplicity, think it is R, okay? And then maybe with some Z. Think of some load actually, not R, some Z, okay? But first draw the phasor diagram. This is VR, this is VY, this is VB. So what is VRY? And this is balanced, okay? Balanced network, balanced three-phase load. So VRY, okay? VR minus VY. So this is minus VY. So this is VRY. So what is this angle? 120 and this is 80. So 60 and this is 60. This is 120. So VRY. And IR, how it looks? How the IR will look? IR will maybe lagging load, small lag, angle is phi. And I told you this angle is 30 degree, this angle is 30 degree. So what is the power? P. Power recorded by W1. V I into
cos of 30 plus pi.
30 plus phi. Now VRMS, okay? VRMS.
VL IL.
VL RMS, IL RMS. YL because RY, okay? And RYR, IR and IL are same. I line, right? So VL RMS, IL RMS, okay? Cos 30 plus phi. And VYB. YB, how it looks? YB means VY minus VB. So VY minus VB like this. VYB. This is minus VB. Similarly, here if you do, what is the angle? What is the current? IY. What is IY? IY is lagging VY by some phi. So this is nothing but the angle between
IY and VYB.
IY and VYB. What is this angle?
30 minus pi, sir.
How you 30 minus phi? Because this is phi, but the angle between VYB and IY, I need this complete angle VYB. Okay, VYB and VB And this one, this was actually how much?
30.
This is 120. And this is 30. This is 30, correct. So this is 30. And this is 30. So 30 minus 5, right? Because this is 30 degree. If you see this angle, and this angle was also 30 degree, and 60, and this is 120. No, something is wrong. This angle was not 30 degree, right? See, what was this? This was Vy. So I did Vyb. I need Vyb. Vyb and Iy. So what is the angle between Iy and Vyb? Can you tell me? Because Vy and Vb is 120 degree, and Vy and minus Vb, if I do, this is 60 degree, right? This much. This is 60 degree. So this is 30 degree. And how much is this angle between Vy and minus Vry? This is minus Vry.
But
This is 30. This is 30. Okay. This is 120. Okay.
oops.
And this one, Vry and Vy, V minus Vry and Vy, what is the angle? Can you tell me? 30 degree, right?
30.
Yes, yes. So this angle, within this angle, I will draw with other color. This angle, I am telling. The angle between Vy and minus Vry. This angle is 30 degree, but the current is lagging Vy by 5. So there is a, if I want to determine the angle between Vyb, okay, and Iy,
30 minus 5.
yes. So what it will be? -30 - 5, right? VL RMS, IL RMS, cos 30 minus 5 or 5 minus 30. Anything you write will be okay. So always remember the angle lag or angle lead are with respect to phase voltages. So VR, Vy, Vb. Angle lag means with respect to Vy, not Vyb. So Vy with respect to Vy, there is an angle lag. And this angle is how much? Minus Vry. This angle is Vy. This is 120 degree. Tell me this angle, how much is it? Vb and minus Vry.
What's that?
This angle, Vb and minus Vry. This is 30. This is 60, 90.
90, sir.
This is 90 degree. That's what I am asking you. And this is 30 degree, right?
Yes.
And how much is this angle? Between Vy and Vyb and minus V.
Vy and Vy 30.
30, okay. And this angle is also 30, right? No, then what is the angle between Vyb and Iy? It is 30 plus 5 is coming. Because phase sequence is RYB, right?
Okay.
Then what will be the connection? Is the connection true that I have done? Yes or no? Just check. You don't mug up, okay? Because
Okay.
what I have, the phase sequence is RYB, right? With that phase sequence, I am still getting 30 plus 5.
Sir, in connection, sir, 1 wattmeter is connected to the
Connected to
B phase.
B phase. Then you don't mug up, okay? Then everything will blow up. Nothing will work, okay? So what was the actual connection? If you see, then this connection is not correct. The correct connection is you have to connect this coil to B phase.
Yes.
Then what will happen? Then your W1 will be VRB and IR. Correct?
Yes.
VYB and IY will be 30 plus 5. And this will be 30 minus 5. Okay? Just check. So just speaking in generalized terms, it will be VLIL cos 30 minus 5 or 30 plus 5 you write down, and 1 wattmeter will be VLIL cos 30 minus 5. So just think about this connection, okay? Whatever connection is there, you just think about this, or just like this, okay? One coil like this, one coil with this, one coil with this, and one coil with the other phase, and the 3 phases are coming. Maybe you do like this, that one phase you connect with R, one phase with connect with B, and one phase you connect with Y. This one. So this connection is true if this connection is true with RYB sequence, then you get these formulas. That W1 equal to this 30 plus 5 and this is 30 minus 5. So it, people generally mark up, but that is dependent on the connection and the phase sequence. Right?
Okay.
Connection and phase sequence. So what is now? You tell me. W1 plus W2. What is that? VLIL into cos 30 plus 5 cos 30 minus 5. What you will get if you add cos 30 plus 5 and cos 30 minus 5?
Then
You
like
VLIL cos 5 into root 3. So that will give you P net, right? Because for a balance system, P3 phase is what? Root 3 VLIL obviously RMS cos 5. And what will you get if you do W1 or W2 minus W1? What will you get? You'll get VLIL sin 5. You do and check W2 minus W1, you will get this. So Q3 phase is nothing but root 3 VLIL cos 5 sin 5. So this root 3 term is missing here.
Yes.
So if I multiply root 3, then what will get? This
3 into
then it will get Q3 phase. But you know that tan phi is nothing but from the power triangle P, Q and S. Tan phi is Q by P. So tan phi is what? Q is giving by root 3 W2 minus W1 divided by P. P is what? W2 plus W1. So if the power factor you need, then you use this formula. Tan phi is root 3 W2 minus W1 divided by W2 plus W1, right?
Yes.
So what if two wattmeters are identical reading, showing identical reading? What is the power factor?
Unity, sir.
Cos phi is
1.
And what if one power factor is showing negative of other? Or W1 is minus W2.
0.5, sir.
How 0.5? W2 is minus W1. This term blows up to 0. Then tan phi is infinity. Phi is 90 degree, right?
Okay.
Now depends whether W2 minus W1 is greater than 0 or less than 0. Okay?
Okay, sir.
If it is greater than 0, then it is plus 90. If it is greater than less than 0, it is minus, because it can be plus minus infinity, right? Because W2 minus W1 will decide the sign. If it is negative, it is minus, it plus. So phi is plus minus 90. If plus 90, what is the, it is capacitive. And minus 90, it is inductive. Power factor angle, I am telling.
Okay, got it.
Because power factor angle with reference to the voltage, it gives us the current nature. So phi, if it is minus 90, the current lags. So it is inductive, right? Otherwise, it is capacitive. So that completes the discussion on the three phase. Simple current finding is same as single phase, right? You just take the voltage impressed across the branch, divide by the impedance, you get the current. And that will happen for all the three phases. So do the calculation for any of the phase because other phases are balanced. So basically balanced RLC, okay? So that will hold true.
Thank you, sir.
Okay, you can just see these concepts and try solving the problems. And if you face any doubt, you can just share in the group or the discussion forum, right? So we can end the session here, right?
Okay, thank you, sir.